Attention is all you need. The 2017 paper that introduced the transformer, the architecture behind nearly every large language model today. The dominant sequence models of the time were recurrent. They process a sequence one step at a time, and that sequential nature blocks parallelization and makes learning long-range dependencies hard. This paper proposes dropping recurrence and convolutions entirely. The transformer is built on attention alone, which lets every position be computed in parallel and connects any two positions in a single step. Here is the full architecture. An encoder on the left maps the input sequence into a representation. A decoder on the right generates the output one token at a time. Each is a stack of 6 identical layers. The core operation is self-attention. Each position forms a query and compares it against the keys of every position to decide how much to draw from each value. Relevance is computed directly, with no distance penalty. Formally, scaled dot product attention. Take the dot products of the queries Q with the keys K, divide by the square root of the key dimension D sub K, apply a softmax to get weights, and use them to combine the values V. Rather than one attention function, the model runs several in parallel. Queries, keys, and values are each linearly projected into multiple subspaces. Attention is applied in each, and the results are concatenated. Why divide by the square root of D sub K? For large dimensions, the dot products grow large in magnitude, pushing the softmax into regions with vanishingly small gradients. The scaling counteracts that. Multi-head attention is the concatenation of each head's output, projected once more. Each head learns to attend in a different representation subspace, so the model captures several kinds of relationship at once. The base model uses 8 parallel heads. With a model dimension of 512, each head works in 64 dimensions, so the total compute is similar to a single full-dimension head. Attention appears in 3 roles. In the encoder, it is self-attention over the input. In the decoder, masked self-attention prevents a position from seeing the future, and encoder-decoder attention lets the decoder attend over the whole input. Between attention sublayers, each position passes through the same small feed-forward network. 2 linear layers with a re-LU in between, applied identically at every position. Because there is no recurrence, the model has no inherent sense of order. So position is injected directly into the embeddings, using sine and cosine functions of different frequencies. The positional encodings are fixed sinusoids. Each dimension corresponds to a sinusoid whose wavelength forms a geometric progression, letting the model attend by relative position. The motivation is computational. Self-attention connects all positions with a constant number of sequential operations and a constant maximum path length, where a recurrent layer needs a number of sequential steps that grows with the sequence. Training used the atom optimizer with a warm-up, then decay schedule, residual dropout, and label smoothing. The models were trained on one machine with 8 NVIDIA P100 GPUs. The results were strong on machine translation. The transformer beat the previously published models, including ensembles, on both English to German and English to French. Concretely, the big model reached 28.4 on English to German and 41.8 on English to French, training for 3.5 days on 8 GPUs, a small fraction of the cost of the models it surpassed. The lasting contribution is the architecture itself. By replacing recurrence with attention, the transformer became parallelizable and scalable, the foundation that today's large language models are built on. Attention is all you need. Self-attention, multi-head projections, and positional encodings combined into the encoder-decoder transformer that reshaped the field.